manifolds, so it wasn't a single band, it was a group of bands, but like in silicon, that group of bands was separated from below, from the core states, and in particular the most important thing is that there was a gap, and so it was separated from the states above. Or even in a metal like lead, even if there is not a physical gap, there is always a topological gap separating at any k points the lowest 4 bands from the upper bands. So there is never a problem of deciding which states to choose. But suppose you are dealing with something like copper. As I told you before, what we have is a parabolic band that comes from the s electrons, and we have flat bands that comes from the d electrons. And you would like to construct Wannier functions for objects like this, but there is a problem. Suppose you want to construct the Wannier functions of the d orbitals, so you know that you have to choose a manifold of dimension 5, and say if you are here, it's easy what to choose, but as you move, you see what do you do when you are around here and there are 6 bands and they are all mixed together. And in reality, they are all mixed together. And so what we are going to do is just, again, adopt a choice for us that allows us to be able to extract a smooth manifold of the dimension that we want. And after we have extracted a smooth manifold, we are going to do the Wannier localizations that you have just seen. So in general, when you are dealing with a metal, or when you are dealing with a complex problem in which you care about states only in a, say, narrow energy window, like you do if you want to construct a solid state Hamiltonian for correlated problems, and you want to separate those from everything else, you need to develop a strategy to separate manifolds. And that strategy is also always going to be in some ways approximate. That is, as in the case of the localization functional, our choice of localization is arbitrary, and changing the localization measure will lead to slightly different Wannier function. And the key issue is that actually we have learned a posteriori that those differences are actually very minor, so it doesn't really matter what the functional you choose, especially for solids. For molecules is a bit more sensitive. Here, we'll make a choice that allows us to sort of separate this entangled manifold, and the choice will be based on smoothness. So the idea is that what we want to do, say if we want to obtain this object will actually be defined as the smoothest object possible that is composed of 5 Hilbert vectors, that is 5 eigenstates at 5 wave function at each k point, and such that a certain measure of smoothness is as small as possible. So as we used localization in the previous lecture to get to the most localized orbitals, now we use smoothness to extract things out, and once we have exfoliated this manifold as smooth as possible, we are going to do a Wannier localization. And since smoothness is also in Fourier sort of analysis related to good localization, this smoothest manifold will give us the most localized wave function. So we are going to look at a measure of smoothness. Before going into that, what I need to point out is that now we have 2 degrees of freedom that we have to deal with. Before, in the case of silicon, we had only 1 and self-evident degree of freedom. That is, it was evident that we wanted to transform the occupied valence bands, and so the dimensionality of our manifold was 4. Now, in this case, the dimensionality of the manifold that we want to extract is more arbitrary. A sort of straightforward choice would be saying we want to extract a manifold of dimensionality 5. But we could want to extract, instead of manifold of dimensionality 3 or 2 if we wanted the T2G or the EG orbitals, or we might want to extract a manifold of dimension 6 that includes all the d orbitals and the s band. Okay, so there is a sort of a degree of freedom on the dimensionality, and then there is a second, more important degree of freedom that has to do with sort of deciding the playing field. Suppose that we have decided that we want 5d orbitals. Okay, so the dimensionality of the manifold is 5. What we are going to do is we are going to extract this from what we have. But the question is now, what are we going to use with to extract this manifold of dimension 5? You see, you could decide sort of graphically that, say, you want to choose only states included in a narrow band here, or you might want to include a slightly larger band, or maybe a larger band. If you wanted a subspace of dimensionality 6, the 5d bands and the s band, you might want to sort of play around, starting from all the states that are comprised in this entire graph. So we call that the energy window. Sort of in the code we have different ways to define it. I mean, the simplest would be just a cutoff below and above of, our playing field, what we are going to manipulate to extract the manifold. And that's a decision that you have to make, and I'll actually show you example of what happens for the case of, the 5d orbitals as we change this, okay? Because generally speaking, the higher this object will be, you will be sort of variationally increasing your degrees of freedom, so you're going to extract a smoother and smoother manifold of dimension 5. If you take everything, you have a complete set of orbitals, you're going to extract something that is completely flat, but it's not going to be physical at all. And as you make this smaller, the manifold will become more dispersive, but will also be physically closer to what you actually want. And I really need to show you the example. So you have to choose the dimensionality n of the manifold, and you have to choose your energy window. And once you have done that, I'll show you what is the disentanglement algorithm. And once you have obtained that, you just apply the recipe of the first lecture to sort of maximally localize that, and that second part is straightforward. So the interesting thing is what do we define as a procedure to extract the smoothest subspace possible, and we actually extract a manifold such that the omega I, defined again here, written explicitly in its reciprocal space representation, is minimal. Now you could say, well, haven't you just explained to us that omega I is invariant, so how we can minimize it? And the truth is that omega I is invariant if we are dealing with an isolated manifold of bands. But now we have a sort of larger set of degrees of freedom, in the sense that we have 6, 7, 10 states at every k points that we are starting with, and we are extracting only 5. And so this omega I is not anymore invariant, and this omega I is going to be minimized whenever this object is as large as possible. And being as large as possible is really a measure of smoothness, because it means that as you go from one state to the nearby, you have maximum overlap. And that is really a measure of smoothness. So the criterion of minimizing this criterion of maximizing this object is really a measure of smoothness. And there is actually a sort of technical term that has been introduced that is the spillage, that is the overlap between, say, the set of 5 orbitals at one k point and the set of 5 orbitals at the next k point. If I go back to this, what I want to extract is a subset of 5 orbitals such that the integral of the spillage, that is the overlap between this manifold and this manifold and this manifold and this manifold, is minimized. And that is really a sort of a global algorithm to track bands by, asking, say, as you sort of move around here, at a certain point you are going to take less and less and less of this band, because these bands start to have a very different character from the D manifold. And so the scalar product that contains a significant part of that band will actually start to be small, and instead you want to maximize it. So maximizing the spillage, maximizing the overlap of this 5-dimensional manifold here and here and here is a sort of global topological recipe to try and extract a continuous manifold that is as similar to itself as possible as you walk around the Brillouin zone. Okay, so it's really a topological measure of smoothness that we implement, for which, as usual, there is an algorithm, and maybe I really will not go into the details of this algorithm, otherwise I'm going to kill everyone with algebra, but sort of, again, what we have, say, is at every k point a 5-dimensional manifold, and we want to maximize the overlap between the manifold here and the manifold here and the manifold here and the manifold here, and so on and so forth. And so we choose really a recipe that maximizes this overlap by taking the highest eigenvectors of the projector operator from one point to the other. Again, just sort of think at it intuitively. We are really trying to maximize overlap, and we are going to do it over all the Brillouin zone. So once we have extracted this manifold, we are going to localize it with the recipe of the maximal localization that we have described before. So let's see what happens in the case of copper when we have a 5-fold manifold that we are going to extract, and what happens in particular as we change our sort of playing field, that is, as we change the number of states we deal with. So we could have an energy window that looks like this in this case, or a much larger energy window. So you see what happens. Well, in these two cases the results are fairly similar, and actually disentanglement and localization gives you exactly the d orbitals of copper as you expected. And in this particular case you actually don't have the degeneracy that I told you should worry if you look at a transition metal oxide in which they are all mixed together. But it's interesting to see what happens when my energy window, say, is narrow, or when my energy window is large. What happens is that the disentangled manifolds is actually smoother and flatter in the second case, because I've systematically increased my degrees of freedom, so I can only do better. But I do better, but somehow less physically, because say at this L point here, you see in this case I've not sort of mixed up states from above here that have nothing to do with my D states, while here that I've chosen a larger window, I've had the possibility of mixing states here. I've made the manifold smoother, but in a way I've made it less physical. There is always going to be an issue, because you see, look at this, look at this problem here. You see, we have a D band here that starts here and then continues here, but in this region is strongly mixed with the S band. So in a way, it's always arbitrary what I'm doing. And if you want, my red manifold is not at all describing correctly the electronic structure of the system in this region here, because you see, the band dispersion of the red manifold has nothing to do with the true band dispersion of the system. I mean, it's the most compact and sort of good representation of these D bands, but in reality, if I want to describe very well everything, a 5-dimensional basis is not good enough. So in many ways, you see that the Wannier functions are really becoming, ab initio, well-defined way to construct a tight binding representation, to construct the localized orbitals that give me the right wave functions. And before let me see, I hope, no. I actually don't have the slide in which I try to do a six-fold dimensional manifold. That's on the paper, but say I could try to do the opposite. That is, I could try to take a larger energy window and ask for a manifold of dimensionality 1. And then somehow this smoothness algorithm, if sort of started properly, that is forced to have, say, these states down here, would sort of automatically choose the smoothest continuation possible, and so it would really follow the S bands. You see, basically identifying it with it exactly where the S band is really a pure S band, and interpolating with it when the S band is very mixed with the D band. And the truth is that for this system, what you really want is both. You want the D bands and the S bands. And I'm sorry I don't have the full example, but I have another example with graphene and carbon nanotubes in which you'll see the same problem. And we can actually sort of play around a lot with these strategies, because now we can even construct, say, Wannier functions that are perfect interpolators of, a certain region in the band diagram, and as smooth as possible a physical interpolator outside. Suppose that for some reasons, again, because I care about effective Hamiltonians, I want to build a very good representation of this region in the band diagram. So I can actually force myself by choosing a sort of large energy window like this, but then asking the coder to reproduce exactly these states. And in the jargon of the Wannier coder, what we say is that we freeze these states, so we don't do any disentanglement. We take them as they are, and all the disentanglement procedure is only taking place in this subspace. And so what the disentanglement is doing is starting from these frozen bands and looking at the smoothest possible interpolator outside this region, and the fact that is the smoothest possible will give rise to the maximal localization, and so it will be as localized as possible, so a very good local description in terms of orbitals that actually do a perfect job of describing the band structure where I want it. It'll become a bit clearer, I think, when we look at graphene in this case, but let me sort of show you a last example of this, one in which, say, I work again with silicon. And we have learned already, if we were to deal with only the 4 valence bands, we could take this manifold, localize it, and we would obtain these covalent bonds. And now what I can do is decide to take a window that goes from the gap, say, up here to this dashed line, and I can try to now extract a manifold also of dimension 4. And if I do that, I disentangle this red manifold from this blue spaghetti, and once I localize it, it's going to look like this. So it's exactly looking like anti-bonding orbitals. So this object creates the 4-fold valence manifold. These objects are creating the lowest part of the conduction bands and describing, if you want, the bottom of it almost exactly, because the bottom of it is purely given by this. As you go up in energy, you are mixed with higher bands. And there is really nothing that you can do in sort of, trying to separate things, because things are mixed to a certain level. What I wanted to discuss now is this second case, in which instead of trying to first localize this and obtaining this, and then disentangling these 4 states and localizing obtaining this, I start from the beginning with an entire manifold like this, and I ask to disentangle actually a manifold of dimension 8. Instead of doing 4 and 4, I take this and I do 8. Actually, sort of, in the language of the code, even freezing this lower manifold, the valence manifold, that I want to be described perfectly. And if I do this, that is, I sort of allow things to mix together and forcing this lower part to be exactly described, what I obtain are objects that are even more localized. That is, the sum of these 8 objects is more localized than the sum of these 8 objects. This could, you see, is still a good solution in a way. It's something that is a local minimum, but there is a deeper global minimum in which the 8 Wannier functions look like this, and these really are atomic sp3 orbitals. I have 8 of them, 4 on one silicon pointing along the 4 covalent bonds, and 4 on the other silicon pointing on the 4 covalent bonds. And you see, linear combination of this are going to give me this or this. This is the bonding combination of 2 pointing towards each other, and this is the anti-bonding combination. But what the code has given us a very compact and minimal representation. That is, we have 8 states, and those 8 states are going to give us the perfect band structure for the valence and the best possible approximation for the conduction. So in a way, they are at the same time the smallest basis possible to describe this manifold, but also the most accurate. And in this sense, they represent, an ideal tight binding Hamiltonian that is derived fully from first principles. And that's what I'm going to describe next. And this actually concluded my first lecture. I guess since you had Walter Kohn at the beginning, I wanted just to show you that when he won the Nobel Prize in 1998, the American Physical Society actually used these Wannier functions to sort of celebrate his prize. Most relevant to this school is that the post-processing code that we use to construct Wannier function is again publicly available, open source at this website, and you'll use it this afternoon. It's interfaced to PWSCF, but it's interfaced to many more codes, of which I know for sure there are Abinit, Castep, Fleur, and others. And also very much the acknowledgements, that is, all this research started when I went to work after my PhD as a postdoc with David Vanderbilt in the Rutgers department. The code was actually rewritten on Thanksgiving Day of 1996, so for many years was known as Turkey.f, 477. Ivo came into the picture. He first became interested with Richard Martin on Wannier functions for his work on the fluctuations of the polarization, and then joined David as a postdoc, and then when we collaborated at the disentanglement part. And then sort of across the years we sort of kept developing, but in particular in the last few years when Arash Mostofi and Jonathan Yates came to the States, working with me respectively and with Ivo, that we sort of rewrote all the code in Fortran 90 and really made the open source effort a priority. And several people since then have sort of contributed. Yang Su Lee in the early stages of the transport calculation, a lot of work there. And right now Nicola Poilvert and Matt Shelley working with me and with Arash at MIT and Imperial College, and Giovanni Canteler at University of Naples are really the people pushing the code forward. So we'll have a new slide with new pictures very, very soon. Okay, so this concludes the theory part, and I wanted to show you some applications. But are there questions up to now on this part? Go ahead.
How are the Wannier functions for metals localized? Exponentially or like one over I?
So exponentially, and the reason is that the manifold is smooth. So so in a way, all the issue about localization in metals has to do, or the fact that Wannier functions and localized orbitals in metals are not localized, has to do with the fact that we ask that question by asking ourselves a description for the occupied subspace. But the moment I sort of extend the problem and I don't force just a description of the occupied subspace, but I allow to use also the unoccupied subspace, I could tell you heuristically that we are going to have exponentially localized wave function. There is no proof for it. I mean, as much as was almost no proof for anything else. But you'll see it actually very beautiful in the case of metallic nanotubes. But even in the case of copper, you see the object that you get is localized. But the issue is that they are really describing a smooth manifold. And anytime you localize a smooth manifold, it's going to be localized. But that's very important for the tight binding Hamiltonians, because we are going to have tight binding Hamiltonians that are short range, even in the case of a metal. Any more questions? Okay, so let me. Let me describe a few applications here. I've already given you some hints on the chemical intuition that Wannier function provide. Again, that part I think is very heuristic, but I mean it's been by far the one that has been more extensively discussed and studied in the literature. What I wanted to sort of discuss instead are issues related to the connection between Wannier functions and the theory of polarization and the theory of magnetization, or the use of Wannier functions to study very large-scale systems, electronic structure, transport properties, and interpolation. And I think I owe this slide to Paolo Umari, that has studied a lot the problem of polarization in solid, actually developing an original approach based on the electric enthalpy. But this is really sort of has to do with the problem of the position operator in periodic boundary conditions, because you see, periodic boundary condition, of course, you are periodic as you sort of circle the whole Brillouin zone or the unit cell, you come back where you were, and the position operator is something that is a straight line, it always goes up, and so it's exactly sort of summarized here. And actually the slides of this, sort of the next 10 slides or so, I haven't done them myself. And since I also not done the physics of it, I just asked David that did both the physics and the slides to give me the slides for the school. And so it's all credit to him. And so I actually start here from the problem of discussing polarization in solids. There is always a citation that we like to make from the Ashcroft-Mervyn textbook that says that polarization is the dipole moment of the unit cell, but that's actually an ill-defined quantity. And it's an ill-defined quantity in a solid because really the electronic charge density is a continuous function. You could think of this as silicon with covalent bonds and ions in here. And so if you ask yourself what is the polarization of that system, you'll see in a moment it's actually going to be an ill-defined quantity if you just look at the charge density. And I actually wanted to show you here a more realistic example that is in which I actually show you the charge density for, say, a very important ferroelectric perovskite like lead titanate, that is a ferroelectric material with a spontaneous polarization at low temperature. And if you look at the charge density distribution, you see it's all a continuum. This is an isosurface, and this is the projection of the slide. So there is, of course, even in a material that for many years was considered purely ionic, there is not a good way to sort of separate charge density with ions. And that's where the problem is, because if we are going to decide to call the polarization as the dipole of the unit cell, you'll see that it's not a well-defined quantity in the bulk. Because suppose that we take this as the unit cell, you see that by symmetry there is a positive charge here and symmetric negative charges around here. The dipole of this unit cell is going to be 0. But if we describe the system with this unit cell, and that's an equally good choice, the dipole of this unit cell is going to point upwards, and if we are going to choose this unit cell, the dipole of the unit cell is downwards. So actually, this is a definition that works for an isolated system, but breaks down in the case of a solid. So what do you do in a solid, since that the charge density alone does not determine the polarization? And that's sort of, it's not really in contrast with density functional theory. It's just that you have to obtain the property from a quantity that is different from the density. And as we had seen before, this is all sort of hidden in the fact that the position operator is not well defined in a solid in its straightforward implementation. And so actually this work came prior to the Wannier function, and it's really had to do with the definition of the position operator and prompted the work on the Wannier function. And really it's taking this alternative definition that I've just shown you before with the blunt identities was holding of the position operator. Instead of taking the position operator as the operator R, we take the position operator as I, the gradient of K, calculated on the periodic part on the block orbitals. And there is some kind of symmetry between sort of, going from the momentum to the gradient, and in this case from the position to the gradient in momentum space. But in reality, this is proven with these blunt identities that I just shown you before. And so the important thing is that this representation of the position operator gives us a well-defined definition from a reciprocal space integral of the dipole moment. And you see it's dipole moment of Wannier functions. And so if we define a polarization as the sum, sorry for the poor quality, of the dipole moments of all the Wannier function, it turns out, and I won't go into the proof of this, that this is actually, well, certainly a well-defined bulk quantity, but it's really the physical quantity that we care about. And the demonstration of this, that is fairly complex, goes under the name of the modern theory of polarization. And it turns out, for those of you that are familiar with differential geometry, that this is really a Berry phase, is the integral of a Berry connection over a closed loop. But sort of intuitively, you see the polarization is given by the centers of the Wannier function. So in a localized representation, the center of the Wannier function are really a classical electron. And if you apply an electric field, the polarization is going to change, and is going to be described exactly by the changes in the Wannier functions. And so, say, we started from this picture, we go into a Wannier function picture in which the electron is given by the Wannier center. And so now we have this picture of the charge density of the system with localized electrons. And when you have that, you can actually define exactly a polarization just as the sum of the dipole given by this charge density. And if you actually look at the math of this, you'll discover that as you change the unit cell, the polarization doesn't change unless you sort of you see the step in which the unit cell is crossing over, the blue comes out from one side and enters from the other sides, and the polarization acquires additional term. And the truth is that polarization is solid is not a single valued quantity, but it's a quantity that is defined exactly modulo this sort of discontinuous jumps that come when one charge enters from one side and exits from the other sides. So in order to calculate the dielectric properties in solids, this is an unavoidable problem. The polarization is a multi-valued quantity, but actually the modulus in these changes in polarization tends to be much larger than the experimental value of the polarization. That is really, if you look at the response of a system to an electric field, usually the shifts are so small that you never have this case. But one needs to pay some care. And we can do this to sort of analyze a bit more in detail the dielectric response of some interesting material that you'll actually see in the hand-on exercises in the afternoon. That is, if we take a ferroelectric perovskite and we look at the dielectric response. So ferroelectric perovskites tend to be systems that are cubic at high temperature with, say, a cation here that could be barium, lead, potassium, that is really just a filler for the structure that has very hard octahedral cages of oxygens in red with, say, a transition metal like titanium or zirconium or niobium in the middle. So these are sort of typical ferroelectric perovskites. And what happens when you decrease the temperature is that a ferroelectric instability arises in which actually the system is more stable, becomes more stable by breaking cubic symmetry and shifting, say, the oxygen cage along one of the possible 6 equivalent directions, say, shifting the oxygen cage up, shifting the titanium down, creating a polarization that is enhanced by the resonance with all the other polarization vector, and getting in a more stable state that has actually a non-zero polarization vector. And if you look at the band structure, say for something like barium titanate, these systems are insulators, and you can actually do the transformation of, you see, all these different manifolds, either one at a time or all together. And the most interesting manifold is the top valence here, this manifold that actually consists of 9 bands that comes from the oxygen 2p's. You see, in the unit cell there are 3 oxygens. The oxygens are ionic, so they suck in electrons from the titanium and from the barium, and so they are, in an ionic picture, sort of filled shell oxygen with 8 electrons sitting around them, of which 6 electrons are p-like. So we have 3 oxygen, each of them with 6 p-like electrons, so we have 18 p-like electrons there, and that means 9 bands. But if we look at the Wannier function of these 9 bands, you'll see that they don't actually look exactly as p electrons should look like, and this is the reason. So these are the top 9 valence bands, and you could say, well, they should really be looking like pz electrons, but it turns out, even if there is a gap, that they have hybridized significantly with the titanium 3D states that sit here at the bottom of the conduction band. And so when you do the valence wave function for this manifold, you get something that looks a lot like an oxygen 2p with significant hybridization with the titanium 3D. And there is, for the pz orbital, a titanium 3D symmetrically above and symmetrical below. So you'll see the Wannier functions actually looking exactly like this. They look like pz orbitals, but with a very strong titanium 3D hybridization. So this is an example, say, of the chemical intuition. Everyone thought that ferroelectric perovskites are ionic materials, but in reality, if you look at the electronic structure of the oxygen, you see that the oxygen bands have a very strong titanium component and a very much covalent-like bonding between titanium and oxygens. And this is the sort of chemical intuition, but you can see the dielectric response of the system being driven exactly by this covalency. Because if you look at what happens when, say, the oxygen cage displaces against the titanium, so here the oxygen, here is the titanium, and here is the other titanium, that is what happens when these bonds become shorter and this bond becomes longer. You'll see, if you look at the Wannier function, that there is a huge charge reorganization. So this bond is really at the border between being covalent and being ionic. So here it's sort of covalent-like. You stretch it, you stretch it here, this weakens a lot, this strengthens a lot. So it's going from covalent to ionic, and in the process, it moves a lot of charge density, so it creates a huge dipole. And we can actually calculate that by looking at what are called the Born effective charges. The Born effective charges are a well-defined physical quantity that is really the derivative of the polarization with respect to a displacement. So, say, if an oxygen atom is really sitting in an ionic crystal, it has, when it moves, 8 electrons on it and sort of 6 plus charges in the core. I mean, all the core electrons and the other protons are screened. So a purely ionic oxygen, when it moves, it should move carrying with itself 2 electrons. So in an ionic picture, the derivative of the polarization induced by an ionic displacement should be equivalent to a dipole of 2 electrons that are moving rigidly. And so the more the electronic effective charge look like the natural oxidation state of your system, the more you are in an ionic picture. And the farther away they are, the less ionic the picture is. But we can calculate this. We know how to calculate the polarization in a solid from the centers of the Wannier function, and so we know how to calculate these effective charges. And if we calculate these effective charges, you see that barium, I told you, was a filler. It's fairly ionic. It has lost its own 5s electrons, and the effective charge is almost 2. But if we look at titanium, that should have a +4, and at oxygen that should have a -2, and we actually calculate it, you see that they are actually much, much larger. These are the sort of giant effective charges of ferroelectrics. And actually, for the ferroelectric material in this configuration, the effective charges of the oxygen are large in this direction, but are fairly trivial in this direction. Because when you move against this, you're sort of in an oxide plane against the barium, and so you look very much like an oxide. But when you move against the titanium, you are shifting a lot of charge, and so the effective charges are huge. And actually, these can be measured not exactly in themselves, but the effective charges really give the splitting between the transverse optical and the longitudinal optical phonons in the phonon spectrum at gamma of a material. And so you can calculate this, and from this and the dielectric constant of the material, you can actually predict what that splitting is. And that splitting is huge exactly because these are large. And the issue is that the longitudinal optical modes and the longitudinal optical modes are infrared active and the transverse are not. And so the coupling with the electric field is very different in the two cases. Please.
Go back to so if you have a non-ferroelectric material like STO, so do you expect the Born effective charge will be very close to the formal charge?
So it really depends. That is, I mean, if you have, say, a system like silicon, there is going to be no polarization induced by displacement because of inversion symmetry. Okay. You take a system like gallium arsenide, and you have broken inversion symmetry, and so you develop an effective charge, and you develop a polarization that is different from zero, but they tend to be much closer to what sort of their usual valence would have indicated.
Okay.
So
you think that this is purely due to the ferroelectricity?
So if you want, the large discrepancy is the driving force for ferroelectricity. The material wants to be ferroelectric and have a spontaneous polarization because a small displacement creates a huge dipole that is cooperative with all the other dipoles. And this is what I was trying to sort of explain. And if you look at the Wannier function in practice, in the paraelectric cubic state, and say, in this case in the tetragonal phase, what you see is that there has been, at least graphically, a larger transfer of charge from one system to the other. Maybe the scale is not identical, but you see how this has become weaker, and this doesn't look that much stronger, but when you actually do the numbers, that is the relevant point, the effective charges are very large. Please.
Computationally, if you create a situation where these paraelectric to ferroelectric transition takes place very near to that, do you see this bond charge will be very big, very small, sometimes random, like a fluctuation?
No, so the sort of exact point at which the sort of ferroelectric and paraelectric phase coexist is a point in which the free energies of the two phases are identical, and so in principle it costs zero free energy to transform ferroelectric in paraelectric. So what would be diverging is the dielectric response of the system, because it costs you zero to go from ferroelectric to paraelectric. So an infinitesimal electric field can create a huge polarization, but that is still with actually effective charges that change only very little. So the effective charges in themselves change very little from one phase to the other, but of course at the phase transition, the dielectric response, that is a susceptibility, diverges like all sort of response function diverge at a phase transition. And then the fact that it's not divergent is only related to the sort of nucleation cost and the fact that there is an interface, and so it's really related to the cost of moving the domain wall boundaries between the ferroelectric and the paraelectric phase. Okay. And so this was the explanation. And again, sort of, this has been used extensively to look at the chemistry of complex objects. These are actually polyvinyl fluoridine, ferroelectric polymers, but in particular this connection with the modern theory of polarization makes the centers of the Wannier functions very attractive. And so all of this was developed by David Vanderbilt and Raffaele Resta in the early 90s and Dominique King-Smith. And this is just a summary of this part with sort of, just reminding you that the polarization in a solid is a non-trivial quantity. And I won't really go into the complement to that is in discussing magnetization, but the problem is somehow similar. If you want to look at orbital magnetization, in principle, again, you don't have a bulk definition that comes from integrating the currents, but in a Wannier representation, you can actually calculate that circulation in a meaningful way. And this is just to cite it. I'm not sure exactly what Davide showed you yesterday, but very much sort of a lot of the recent developments that we are making on the sort of calculation of NMR spectra and EPR spectra, that is the response of a system to an applied magnetic field, sort of can now be recast in terms of Wannier functions and what is now become known as the modern theory of magnetization, again developed by David Vanderbilt and Raffaele Resta, together with Davide Ceresoli, that is here, and Timo Tonhauser, and equivalent developments made by the group of Chiang Nhu at University of Texas. And so as much as you have seen a sort of 15 years of study of ferroelectric and piezoelectric and dielectric properties of materials, I think these recent developments will really push the developments of the description of magnetic properties of materials, and this is very much an area of work. Okay, so this was the first part of the second lecture, that is discussing the connection with the theory of polarization and the theory of magnetization. And the last part that I wanted to focus on it is on Wannier functions as a tight binding basis that is accurate, that is derived from first principle, and that allows us to construct the electronic structure or the transport properties of very large scale systems, or it allows us to calculate very accurately integrals that depends very sensitively of what the states are doing, say, just at the Fermi energy. And I'm sort of taking here an example from some recent research of us in which I say we wanted to look at the electronic structure and the transport properties of systems like functionalized carbon nanotubes in which, say, you have a very long metallic carbon nanotube that has been decorated with organic molecules that have that are covalently attached. And so typically a system like this would contain tens of thousands of atoms, and what you care about, say, is a transport property, like what is the probability for an electron coming from this side to be scattered back or to go through. This is sort of what is called in the solid state the Landauer ballistic conductance. And if you wanted to study this system using any electronic structure code, you would be killed by the costs of studying tens of thousands of atoms. And I'll show you how you use Wannier functions to actually sort of get to an accurate representation of data with costs that are basically linear scaling. And the basic idea is this. That is, if you are forced to use a block representation for a huge system like this, you will have a huge number of block states, and you have to do a calculation, say, on this supercell. But suppose for a moment that you do a calculation on a smaller supercell, like this object here, periodically repeated. So this is something that your ab initio code can deal with. It probably contains 200, 300 atoms. But when you look at your states, not in the block representation, but in the localized representation, it turns out that states here will look sort of very different from a pure carbon nanotube state, because there is a lot of chemistry. But states away from the residue will look like a pure carbon nanotube Wannier function. And so by having the Wannier function of the pure tube, and by having the Wannier function of this object periodically repeated, you can sort of construct and mix and match an Hamiltonian that describes this entire system, but because all these states are localized, this Hamiltonian is diagonally dominant and can be inverted or diagonalized with linear scaling approaches. And so the idea is this. We do ab initio calculation on periodic objects that are manageable, a few hundred atoms. We use the localization procedure, and we obtain things like this. And these are really like Lego bricks. So these are the building blocks of the electronic structure of the system, because this will be, say, the building block for the carbon to molecule. This is a phenyl derivative ligand, so carbon to carbon sort of single bond here. And then there will be building blocks of, say, the carbon nanotube nanostructure that close by here will be affected by the presence of this ligand, but as you go away, they start to be exactly like the building blocks of the perfect nanotube. And so you can construct an Hamiltonian by sort of putting together all these orbitals and all these matrix elements. And we actually sort of, do this defining what are called the principal layers, that these are fragments of the nanotube large enough so that there is no overlap between one supercell and the supercell next to the first neighbor. And this is just a definition, but once we have this definition, basically our Hamiltonian for that infinite system is going to be bounded because there are going to be no matrix element between anything here and here, or anything here and here, and so on and so forth. And when things are bounded, you can diagonalize them efficiently. And I won't go again into the algorithm and the sort of theory of how to construct the transmission coefficient for an electron that goes through a nanostructure based on the Landauer formulation. Supriyo Datta, I think, to my knowledge, has been the person that in the sort of last 20 years has most worked at this, and there is a very nice formulation by Marco Nardelli, and then Marco Nardelli and Jean-Luc Fatebert and Jerzy Bernolk in the context of electronic structure algorithm, and then in particular we have sort of put it all together in the Wannier representation. But the bottom line is that if you have these Wannier orbitals, you can construct a sparse Hamiltonian, and from that sparse Hamiltonian you can construct Green's function and self-energies and all the ingredients that are needed to construct a transmission probability for an electron to come from the left and either be reflected or being transmitted. And that is really what is called the ballistic conductance in the Wannier, in the Landauer formulation. So how does that look for our case? Well, we are going to deal with carbon nanotubes. And as you probably know, carbon nanotubes can be metallic or insulating depending on their chirality. This is the Fermi energy, so this is the typical band structure of a metallic nanotube. That is what we care about. It really looks like graphene with this sort of dispersionless Dirac linear bands here. And this would be the band structure of a semiconducting nanotube. And they can actually all be derived from the band structure of graphene, you see, with the hexagonal Brillouin zone and these cones sitting at each of the 6 corners of the Brillouin zone, because a carbon nanotube, from the electronic point of view, is to a large extent just a graphene sheet that has been folded and so has been made periodic in one dimension, and it's been sort of been quantized in one dimension, because now you're going to go around the nanotube and you're going to go back to yourself after 8, 10, 20 unit cell. And that quantization in one direction really means that this 2-dimensional band structure has been quantized, and depending on how it's been folded, we are taking the cuts according to the folding. And a metallic carbon nanotube is one in which, say, in this case, an armchair has been folded so that the cuts go exactly through the cones. And so you see these cones here that come from these 2 points here, and then all the other mini bands folded. And in this case, a semiconducting nanotube folded in the other direction, and with a number of cuts here, such that you don't cross the cone, and so you actually have a gap, because the band structure here and the band structure here will be a cut of the cone away from the vertex, and so it will have a gap. But we'll focus on metallic nanotubes, band structure like this, and we could take these objects and do, say, a localization of the occupied subspace. Say, if we look at the semiconducting nanotube, we take the entire manifold below, say, this value here, and if we look at the metallic nanotube, say, we could decide to take all the states that are below the Fermi energy. This is actually mathematically well defined. So how many states we are going to have? Well, each carbon atom has 4 valence electrons, so it will give rise, because of spin degeneracy, to 2 orbitals. So we are going to have 2 orbitals per carbon atom, and if we look at what we obtain, you see we obtain 1 orbital for each bond, okay, and each bond is shared by 2 carbon atoms, and then we are going to have 1 orbital every 2 carbons. You see, this looks like a pz orbitals, sort of delocalized. Okay, so these are the orbitals that we obtain, 2 orbitals per atom, if we just do a localization of the occupied manifold. And if we look at how these things work, you see that it actually works very well for the low part of the spectrum, but it actually, in the metal, works really poorly around the Fermi energy, and even for the insulating nanotube, the interpolation